Welcome to Climate Now. I'm James Lawler, and this episode is the first in a two-episode series on NASA's Orbiting Carbon Observatory, abbreviated OCO. These are missions to collect global measurements of carbon dioxide in our atmosphere from space. Today's guest is Dr. David Crisp, a senior research scientist at the NASA Jet Propulsion Laboratory, JPL, and the science team lead for the OCO2 and OCO3 missions. David also serves as JPL Task Force Lead for Earth Ventures Geostationary Carbon Observatory, abbreviated GeoCarb, which will launch early in the 2020s and will expand on the OCO mission measurements. David, welcome to Climate Now.
Good to be here.
So David, let's start with the same question that we ask all our guests first, which is, how did you get to where you are today in your career?
It's a long, winding road that brought me from a government-subsidized housing project in a Texas border town through Texas A&M University, where I got a degree in education. I wanted to be a physics teacher. Through Princeton University, where I got a PhD in a field called geophysical fluid dynamics, the study of the transport of winds and oceans around our planets. To Caltech, where I was a postdoc and got to fly balloons with the Soviets and the French in the atmosphere of Venus. To the Jet Propulsion Laboratory, where I've been able to work on things like the Hubble Space Telescope, helping to build the camera that fixed the Hubble aberration, helping to build weather stations for our early Mars landers, like Pathfinder and the ones that immediately followed. I got to then also learn a lot about ground-based astronomy, making measurements primarily of the planet Venus. So for the first maybe 20 years of my career, I was actually a planetary scientist.
And how did that lead you to studying the climate here on Earth?
I was studying the climates of the planets Venus and Mars with a particular fascination with Venus. Why did this planet, which was supposed to be Earth's sister planet, it has an atmosphere that's basically about 100 times as dense as the Earth's atmosphere, and it's made of carbon dioxide. And Venus is a little bit closer to the sun than us and receives about twice as much solar radiation. But it's covered by these super bright sulfuric acid clouds. The entire planet is. And so it reflects 80% of the sunlight that hits it. And so it actually receives only about 70% as much sunlight as the Earth does. Why is its surface temperature almost 850 degrees Fahrenheit? Well, it's driven by a massive carbon dioxide greenhouse. We've been making carbon dioxide measurements in the Earth's atmosphere since 1958, regularly, since Charles David Keeling actually installed sensors at Mauna Loa Observatory in Hawaii and at the South Pole and started making measurements there. And that network has now grown to about 200 stations. And we've been making progressively better and better measurements of carbon dioxide around the Earth. And what we've been seeing is over time, the amount of carbon dioxide in the atmosphere was just increasing and increasing and increasing. So it was hard for me as an atmospheric physicist, as an observer, to miss these things. As I looked into it a little bit further, it was really not surprising at all to find out that the carbon dioxide abundance of our atmosphere was increasing because we were burning fossil fuels and we were deforesting the world. All of these processes were contributing to the buildup of carbon dioxide in our atmosphere. But that wasn't surprising at all. What was surprising, to me at least, was that I learned that only about half of the carbon dioxide we put into the atmosphere every year, and it was about 25 billion tons of carbon dioxide at the turn of the century. It's 40 billion tons today. Only half of that carbon dioxide was staying there for more than a year. The rest was either being absorbed in the ocean. CO2 dissolves in water to make carbonated water. We were carbonating our oceans. Another quarter of it was disappearing somewhere into the land biosphere, into the forest, into the fields, being absorbed as a part of the photosynthetic process as plants absorb sunlight and carbon dioxide to make those roots and stems and leaves. They were sequestering, stealing half of the carbon dioxide we were dumping into the atmosphere every year. But I was also astounded to learn that nobody knew where or why the oceans were continuing to absorb more and more carbon dioxide. Why the land biosphere was absorbing more carbon dioxide. Where were they absorbing more carbon dioxide? With a couple hundred ground-based stations measuring carbon dioxide, we could tell it was going up or coming down, but we couldn't tell you where or why.
And so how did you wind up leading that effort to try to answer why and how the trees and the ocean were absorbing more carbon dioxide?
At that time, I was actually the lead of a NASA technology program trying to design the next generation of instruments to study Earth, to study planets, to study stars. And one of the things we started looking at was, could we measure carbon dioxide and other greenhouse gases like methane from space with the kind of precision needed to identify the sources emitting them into the air and the natural processes pulling them out of the air? Some of these systems that we were using every day to observe the planet Venus or Mars, high-resolution spectrometers that take light and divide it up into a rainbow of colors, and then look at the amount of light in each color very, very precisely and measure the amount there. Different gases like carbon dioxide and water vapor and oxygen and methane all absorb only certain colors of light. And so if I see those colors missing, whether it's in the atmosphere of Venus, the atmosphere of Earth, the atmosphere of a distant exoplanet, I know it's carbon dioxide, or I know it's methane, or I know it's water vapor. Could we use that kind of technology to measure carbon dioxide in the Earth's atmosphere? So I took some of the models that I had developed for studying the atmospheres of Venus and Earth and Mars. I found out what measurements I needed, and I came up with a concept. And a couple of my colleagues at JPL came up with other concepts. And we basically had a knockdown drag out and tried to, basically figure out which concept will work better.
So JPL actually had a competition.
An internal competition, very friendly, and it was really just a matter of which one of these methods is going to work best today, and which one's going to cost the most, and which one's going to cost the least, and so forth, and which one's going to be the most difficult to implement, the easiest to implement, which one is going to produce the best data.
Got it.
And the concept that kind of fell out of that whole process seemed to be the one that I had developed. So I was asked to lead the effort. But then we still needed to actually get the funding to make this happen.
How does it work at JPL with these space instruments? I mean, do you have a sense of what it will cost, or do you get a certain amount for just, I don't know, R&D, and then you tell them what it costs later? Roughly, how does this work? Getting the budgets to make a new space instrument.
Basically, to start with, NASA flies spacecraft in two different modes. One are these big directed missions, they're called, where we're actually directed to go and build something that meets some specific characteristics and satisfies the needs of a specific customer base. You can think of the weather satellites as something like that, right? NASA actually builds them. We then transition them off to NOAA. They use them to predict the weather. Okay, so there are these big systems. But NASA realizes that while these systems are being built, we're learning new things about the planet all the time. New needs develop, new capabilities develop, things that we need to do that we couldn't measure. So NASA has another program, and the program is an individual Principal Investigator-led program. So individual scientists make a proposal to make a specific measurement, and then they make a case for making that measurement. And they say, we need to make this measurement, we know how to make this measurement, we know how to build a system that can make this measurement, and we think it'll cost this much. If that's selected, then you get to put in a bigger proposal, 450 pages, big notebooks full of writing that go into detail about every aspect of the mission. Those programs are very stringently cost capped. The basic way that they go forward is NASA says, you have exactly this many dollars, and you have this much time. What can you do? So that really caps how much you can do in these small Principal Investigator-led programs. And that is, in fact, the story of OCO and OCO2 and OCO3.
Great. So tell us that story then. Some amount of budget was approved and you set to creating OCO1. What was the process of building the Orbiting Carbon Observatory?
The immediate obstacle we hit was that NASA did not have the money to start funding the program. So they said, you're selected, wait a while. So we basically had to stand down for about 2.5 years before NASA really had the resources to start the program. And I had to keep the team together for that period of time and continue to make progress on this. So we started designing the system. And that gave us a little extra time to design. Between 2004 and 2005, we started finally getting significant resources so we could bring engineers into the game, bring a real management team into the game, bring the whole system together and start really doing the detailed design of a satellite instrument, of a satellite to carry the instrument, of a launch capability, of an orbital plan, a plan for going into orbit and what orbit we were going to take and that kind of thing, how we were going to bring the data down. We ran into a series of obstacles and challenges, technological obstacles, more cost obstacles, everything you can imagine that could go wrong did. Murphy's Law works full-time in space. And by the way, along the way, the Japanese got a mission that also measured CO2. So in 2004, just as we were getting started in this business, the Japanese approved a mission called GOSAT, the Greenhouse Gases Observing Satellite. It was a Fourier transform spectrometer. OCO was a grading spectrometer. These used different measurement technologies that were right at the precipice of the cutting state of the art. And if we worked together, we could combine the results of these two systems to eventually learn a lot more about the planet and how it was actually working. And that sounded like a great idea. So as the leader of the OCO project, I instantly became involved with the Japanese GOSAT mission. And they became partners, and we also started a little competition. Who gets to the launch pad first? So we had a little race going on, but we continued every year to collaborate on the science, on the calibration of the instruments, everything we could exchange legally without, export licenses and so forth, or even with export licenses. We did. We were two separate projects, and we were on different courses, and we continued to have our own sets of challenges. Our management was yanking us forward to stay on schedule, to stay on budget. They were really pushing hard. We were actually being asked to essentially invent on a schedule to get past problems that we overcame, that we encountered along the way. And it was an incredibly grueling 80-hour weeks, solid, for this group of people. In 2009, we both finally got to the launch pad. They beat us by a month.
The management was doing that just because that's how management at NASA works, or they didn't want to get beaten by the other project?
It's because that's how NASA management works. We did not want to run over our own budgets, because when we run over our own budgets, as I told you earlier, OCO was delayed several years because NASA didn't have the money. Why didn't NASA have the money? Other programs overran their budgets as they were being prepared and essentially ate our budget along with their own. So it was an internal process that drove both missions forward, and it was, in fact, somewhat of a coincidence that we arrived at the launch sites 1 month apart. So then our chance finally came. We finally got to Vandenberg Air Force Base on our Taurus launcher on the 24th of February, 2009. And we had a launch at about 2 o'clock in the morning. It looked like a great launch. We basically, those of us on the ground, I was in the control center, everything went absolutely beautifully for the first 3 minutes and 53 seconds. If you're not nervous when something you've been working on for 9 years, that you've invested 1,000 work years in, if you're not nervous, you don't have a pulse. It's a nerve-wracking activity anytime you're doing a launch. But we had checked and double-checked and triple-checked everything. And we thought we were ready to go. So as I said, we launched. It looked beautiful, cleared the tower, went all the way to the horizon, looking just absolutely beautiful. At night, you could see the rocket, all the beautiful arc it made across the sky. But 3 minutes and 53 seconds into the launch, the fairing, the pointy end of the rocket is supposed to open up because you're above most of the atmosphere now, and you don't need it anymore. And you can't really carry that weight all the way to orbit with you. It was supposed to open up. It didn't. So now the rocket is flying. The spacecraft is trapped inside of this fairing. It can't go anywhere. The rocket, with that extra mass, made it all the way to its target altitude of about 610 kilometers. So about twice the altitude of the space station. But it was going too slow. It's supposed to be going 7 kilometers per second to get into orbit. It was only going about 6 kilometers per second because it was carrying the extra weight. I was watching a screen and they had feet per second on the screen, and I was converting it in my mind to meters per second and kilometers per second so that I could understand what the evolution of the system was. And I started seeing numbers that I just didn't understand as this was happening. So I turned around to the head of the launch vehicle group, and he goes, "I'm sorry." And within 10 minutes of the launch, we had re-entered the atmosphere at hyper-Mach speeds. The tiny bit of material that didn't burn up hit somewhere in the Indian Ocean just off the coast of Antarctica, probably scaring a few fish. 1,000 work years. At that point, $270 million was over. No data, nothing. So that wasn't my best night, to say the least. But some good things happened. Within minutes, the head of NASA Earth Science, who was also at the launch, came to me and said, "Dave, keep the team together. We're going to find a way to do this again. We don't know where the money's coming from. We need to go and start looking." I said, "Yes, sir." Then, as the sun was rising, my Japanese colleagues, who were my guests at the launch, came to me and said, "Dave, you have a great team. Come and work with us. Let's learn together how to process space-based measurements of carbon dioxide." And I spent the next 10 months with my colleagues throughout NASA, throughout the academic community in the US. We had help from our international partners, trying to find the money to do this again, and failed. In November of 2009, Mike Freilich, the head of Earth Sciences at NASA, came to me and said, "Dave, we didn't do it. We failed. We fell short. We're going to have to do this again next year." And that didn't sound very good, but I said, "Yes, sir, we'll do it again." And by the way, you'll remember 2009, we were in the depth of the greatest recession since the Great Depression. And I'm walking around asking for $250 million. It's like Oliver in the movie walking up with the oatmeal bowl saying, "Can I have some more?" And you can imagine the reception that I got for 10 months as I talked to everybody in power in the US Congress and throughout the rest of the federal government.
So are you ever thinking to yourself, maybe I should just quit?
I don't think that way. I have this strange sense of duty.
Duty towards what, would you say?
It starts out with maybe my planet, maybe my species, maybe my government, maybe my agency, maybe my company, maybe my group, maybe my family. What we were trying to do, we thought was critical for understanding the health of our planet. So it really did start from top down. So I wasn't going to let them down. So that was what drove me forward. Then we had the Copenhagen Climate Conference that some of you will remember in December of 2009. And it was the first of these meetings that Barack Obama attended. And he went there with a really strong motive to try to get the countries of the world to come together. We did not sign up to Kyoto, but we were going to sign up to the new climate treaty that basically said that we will try to minimize the kinds of climate change that could be destructive. And so he got to the climate conference, very enthusiastic, and he just hit one obstacle after another. People really did not want to sign up to making measurements of carbon dioxide, controlling the amount of carbon dioxide emissions, and they certainly didn't want things like on-site inspections and the other things you have to do to put a treaty in place. The Chinese premier at the time, I understand, literally handed Obama his hat and walked him to the door and said, "No, sir." I'm at the American Geophysical Union conference in San Francisco at that point, during December of 2009. At 3 o'clock in the morning, I get a call from the White House. "Dave, get your team together. We found some money. You're going to build another spacecraft to make measurements of CO2 from space because they're not going to let us do it from the ground."
So that conference and the fact that we couldn't get the treaty done, we couldn't get that to happen, that drove the desire to fund your program.
Yes, because we could not come up with a way that was considered to be a fully transparent, equitable way to monitor emissions of greenhouse gases, nobody would sign a treaty. And so the question is, are there other ways to measure carbon dioxide and methane and other greenhouse gases?
And they were like, "We know this guy."
And yeah, exactly. I had been working with them all year long, and they said, "We know this guy who knows how to do this. Maybe we want to give him a shot. How much is it going to cost?" Oh, it's a tiny amount of money compared to the U.S. government. It was a tiny, tiny amount of money in terms of a national program. But once again, it actually filled an urgent need. But we were given a specific set of requirements. And one of those requirements are you have to fly within 3 years. So you better get ready and run. You better be ready to hit the ground running and get this thing out. And you're just making a carbon copy of this thing, so just get it done. So we got to build item 2. Now, this is something we almost never get to do in NASA. But what we do know is that item 2 almost always costs more than item 1. It's always easier to start from a clean sheet of paper and use the available capabilities and technologies and put them together than it is to say, okay, now I've got this complete set of plans using technologies that are 10 or 15 years old. How am I going to buy those technologies? What happens if the price goes up over time? And it did. So the second version of the system came out costing about twice what the first one did. But it was actually worth it because I was given another order at that time, which was, and by the way, you're not going to build one of these. You're going to build 2. You're going to build a flight model and a flight spare, just in case something goes wrong the next time. And oh, by the way, you're going to fly on the same rocket you flew on before. And I'm like, oh my God, that's not going to work. But the company that made the rocket was sure they would be able to fix the problem. Well, we're building OCO2 and we're working as hard as we can and we're pushing the teams to meet this 3-year deadline. And the company that built the rocket thought that they had fixed the problem. And so they launched another incredibly important Earth science spacecraft on that rocket in 2011. And it failed in exactly the same way that the OCO rocket had failed. Okay? So that rocket was taken out of service. Well, guess what? We didn't have a rocket now. So we had to redesign the system and adapt it to fly on a new rocket, but we also needed a rocket, and we didn't have one. But there were these 5 old parts queens of a line of very reliable boosters called Delta II. There were 5 of them left. The program had been shut down in 2008 for building these things, but there were 5 left, and they had been picked over for parts for 20 years. The question is, out of those 5, NASA just bought them all. And they said, we're going to be able to build 3 good rockets out of this. I got the first one. So this is a big rocket. And it was an expensive rocket, and it ran the cost up again, okay? But it was a reliable rocket. That was the main thing that we knew about it. So it caused a delay. We had to wait an extra 14 months for them to finish this rocket. So what they did was they forced us to finish the OCO2 payload, the instrument and the spacecraft on schedule. And then we put them into storage for 14 months. And then when the rocket was finally available, we put it on the rocket, we put it on the launch pad, maybe 2 football fields away from the one we had launched OCO on. And on the 1st of July of 2014, we were ready to launch. And the launch was canceled like 40 seconds before it was supposed to go off because the water sprinkler system that suppresses sound associated with the launch, which otherwise the sounds are so loud that they break things, right? So we spray water on our rockets so that it basically reduces the sound levels. Well, they found the problem the next morning. They fixed the valve, and we were ready to go the next day. And so on the 2nd of July of 2014, we had another launch from Vandenberg. It wasn't like the first launch with a perfect night, crystal clear, everybody out making nice photographs. It was a rainy, drizzly night with a low cloud deck. We could barely see the rocket from a little ways away where the cameras were set up, but we could hear the roar. And it was a perfect launch. And the rocket deposited us within, exactly the target zone we wanted to be in the orbit that we needed to be in. So much so that we had brought a lot of fuel up in the spacecraft itself to adjust our orbit. We now have fuel through 2030 or something because, we have this big tank of fuel we didn't need to adjust our orbit with. So everything worked fine. We're in orbit with OCO2. And because we had been working with our Japanese partners all of this time, and our science teams had been working with their colleagues and using that data and analyzing that data, we were ready to hit the ground running with the processing of the data. So by August of 2014, we had our very first data down from the spacecraft. By September, we were putting down a regular science product, making 1 million measurements a day, producing roughly 100,000 cloud-free measurements of carbon dioxide around the Earth. About 100 times as many measurements as our Japanese colleagues were making. They were making about 10,000 measurements a day. We were making about 1 million measurements a day. Okay, that's the difference between the two technologies. Okay, a giant step up in terms of resolution and sampling density. Okay, so we could study different things. So even though we had learned some things from the Japanese mission, now we started focusing on our own mission, and we encountered our own share of challenges as we went forward as a science team, learning how to analyze the data from this brand new sensor. Over time, over the next few weeks and months, we got it up and running. We understood the data. We were getting excellent data, and we started learning about the carbon cycle.
Wow, what a story of perseverance and what it takes. Because really, that's what it takes to do anything that's big and challenging. Well, David, I can't thank you enough. Really appreciate your time today and telling us your story and the story of this science and what is possible and where it's all going.
I'm glad that I could contribute.
That was Dr. David Crisp, a senior research scientist at NASA's Jet Propulsion Laboratory and science team lead for the Orbiting Carbon Observatory 2 and 3 missions. Orbiting Carbon Observatory 2 and 3 scientists continue to collect vital atmospheric carbon dioxide data that are changing our understanding of our own emissions and the carbon cycle. Check out part 2 of this series on the OCO missions to hear from Dr. David Crisp and OCO project scientist Dr. Anne-Marie Eldering about what we've learned from the OCO missions. To learn more, access OCO data, or to check out their latest research, visit ocov2.jpl.nasa.gov or ocov3.jpl.nasa.gov, ocov3.jpl.nasa.gov. That's it for this episode of the podcast. You can check out our other interviews, watch our videos, and sign up for our newsletter at climatenow.com. If you'd like to get in touch with us, you can email us at contact@climatenow.com or tweet at us at weareclimatenow. We hope you'll join us for our next conversation.